All right. So let me move my face out of the way. There we go. All right. So this is the second, sorry about that. This is the second set of notes on gases on chapter 10. I'm going to look at a couple practice problems here. I'm going to get a little bit more in depth with gases themselves. All right. So if you think back to where we kind of stopped in the last lecture, we were looking at the molar mass of the gas, the ideal gas law. And this one, we're going to start with the ideal gas law. We're going to look at PV equals nRT. So a balanced equation gives us the relative amount of moles in a reaction, just like it says there. So if you know the amount of moles in a reaction, if you have the balanced equation, then we can relate that to the volume for gases as well, right? Since the number of moles and the volume of a gas are proportionate, then, if we know one or the other, we can calculate the unknown. If you think back to the stoichiometry that we did last year with PV equals nRT, a lot of times we were just solving for N there, and that's not really going to change. Now, some of the laws that come from this that go with that proportionality include Dalton's law. So Dalton's law says that if you put two gases in a container and they don't react, right, they're non-reactive or they're inert, then they will act as if they're alone, okay? They'll not engage in any kind of chemical process. Instead, they'll just bounce off of each other. When you try to account for that, we come up with Dalton's law of partial pressures, which says that the total pressure is equal to the pressure of gas 1 plus the pressure of gas 2 plus the pressure of gas 3. Now, last year when we looked at this gas law, we didn't really do anything with it. We looked a little bit at like collecting gas over water, and we talked about, without calling it a manometer, we talked about the manometer. But in AP, we're going to look at it in a little more detail. So this is a pretty common problem that we might see that goes with Dalton's law. So it says a mixture of 6 grams of oxygen and 9 grams of methane is held in a 15-liter vessel at 0 degrees Celsius. Find the partial pressure of each gas and then the total pressure in the vessel. So in order for me to kind of work through this, I need to know a couple things. First, I need to calculate the number of moles of O2. All right. And in order to do that, I'm going to take the information in my problem. I'm going to start with that 6 grams of oxygen. All right. And I'm going to convert that into moles. I know that O2 is about 32.0 grams in a mole of O2. And when I do my math, I'm going to get 0.188 moles of O2. All right. I can now use the pressure of oxygen, okay, which is equal to N of O2 times RT over V, right? This is my PV equals nRT equation. And now that I know the number of moles of O2, I can plug that in. So I'm going to get 0.188 moles of O2. There's N. My R for this equation is going to be 0.0821. I know that because I have liters, okay? I've got moles, and that's going to kind of work out there. And I'm going to do this problem in atmospheres because since the problem didn't give me a set pressure that wasn't atmospheres, I think atmospheres is probably the easiest one. So this is liters times atmospheres times mole inverse times Kelvin inverse. Now, just a quick note on why we write units. The problem gives me 0 degrees Celsius. If I tried to plug 0 degrees Celsius in for temperature, I'm going to get 0, right? Anything divided by 0 is 0, anything times 0 is 0, and 0 divided by anything is 0. So Kelvin reminds me, hey, I need to convert that Celsius over into 273 K. And I'm going to divide this, wow, worst division line ever, by the volume, which in this case is 15.0 liters. Now we'll notice liters cancels, moles of O2 cancels, Kelvin inverse and Kelvin cancels, so I'm left with atmospheres, which I'm looking for a partial pressure, so I should have a pressure volume, or a pressure unit rather, PO2. When I plug this into my calculator is then 0.281 atmospheres. So that gives me my answer for O2. So it says each gas though, so I need to do the second one. So to do the second one, I'm going to do the same thing. I have now N sub CH4, right, the number of moles of methane, and that equals 9.00 grams of CH4. Again, I'm just going to convert. So 16.0 grams of CH4 in a mole of methane. That's going to give me 0.563 moles of CH4. There we go. All right. I'm going to plug that into the PV equals nRT equation again. Right. So I know PV equals nRT. I'm looking for pressure, so I'm going to divide both sides by volume. Pressure equals nRT over V. So the pressure of CH4 is equal to 0.563 moles of CH4. All right. I'm still going with the same R value, 0.0821 liters times atmospheres times mole inverse times Kelvin inverse. It's still 273 Kelvin, right? Because I still have 0 degrees Celsius. It's still 15.0 liters. Liters cancels, moles cancels, Kelvin cancels. I'm left with atmospheres. So PCH4, when I run my math problem, gives me 0.841 atmospheres. So that's the partial pressure of CH4. This is the partial pressure of O2. It also asked me to find the total pressure. Well, the total pressure is a function of Dalton's law of partial pressures, which just says add them together. So I would say that the total pressure, P sub T, the total pressure, is equal to the sum, right, of P1, 2, 3, so on and so forth. And so my first pressure was 0.281 atmospheres. My second pressure is 0.841 atmospheres. Atmosphere and atmosphere, I can add those. They're like terms. So the total pressure, PT, is equal to 1.122 atmospheres in the vessel. And that's how I do those problems. Okay? So moving on. Some other things that we can do from PV equals nRT is calculate what's called the mole fraction. Since those inert gases, since those gases that are not reacting are acting as if they're alone, we can relate the amount in the mixture to their partial pressures, amount in this case being N, right? And so I have the N1, this is the gas I'm looking for, next over the N total, right? The total number of moles. Total pressure, gas I'm looking for, right? Moles I'm looking for. Well, R, T, and V all cancels, so I can say that P1 over PT equals N1 over NT. P1 over PT equals N1 over NT. So the pressure is related to the number of moles. You can take this and calculate something we call the mole fraction, X sub 1. So the moles of compound 1 over the total moles, which is N1 over NT, is equal to the mole fraction, all right? So that equals X sub 1, something you can look for. You can plug those in together, and you can get pressure 1, right? We can solve, equals N1 over NT times the total pressure, equals X1 over PT. So we can calculate the mole fraction that way. This is not one that we're going to see a lot of. It's a useful kind of derivation if you go further in chemistry. I'm not going to work one of these right now, though, because it's just basic algebra. So I think you guys can handle that. Now, when we talk about gases and we talk about PV equals nRT and we look at all these different laws like Charles' law and Boyle's law and Avogadro's law, we're actually describing a larger set of observations. And the thing that we're describing is called the kinetic-molecular theory. And KMT tells us that under certain conditions, gases are going to behave in a certain way. And most of these kind of observations are self-explanatory, right? You squeeze a balloon, you feel it pressing back the more you squeeze, right? This is the kind of stuff that we are trying to explain. Now, in KMT, we have like 3 or 4 major tenets, or 5 major tenets. Number one, gases are huge numbers of molecules, and they're all moving at random. So they're bouncing off each other, bouncing off the walls of their container. They're trying to expand. All of the volume of the molecules of the gas we treat as if it's 0. All right. Now, this little tenet right here, really important, because it's going to change the way that real gases behave, because ideal gases have 0 volume. Well, they really have volume in real life, so there's no such thing as an ideal gas. Like, that's what that means. Number 3 is also important. In the KMT, in the kinetic-molecular theory, we treat the attractive and repulsive forces between gases as non-existent, right? Negligible. We say that, the van der Waals forces and the dipole-dipole attractions and the dipole-induced dipole attractions don't impact movement. That's just not true, okay? The theory is great for predicting behavior, but it does require some of these assumptions. Number 4, all right, another tenet, says that energy is transferred between molecules, like when they bump into each other. So this molecule is moving fast, this molecule is moving faster. When they hit, momentum is transferred. Even though that happens, we assume that the average kinetic energy of the molecules doesn't change over time, as long as the temperature remains constant. So as long as the amount of heat energy being input is the same, even though specific atoms may lose or gain momentum, the overall average kinetic energy doesn't change. And then we assume that the average kinetic energy of the molecules is proportional to the average temperature. So we would say that as the temperature increases, the average kinetic energy would increase. And we can see that here in this graph. So we have molecular speed at the bottom. On the x-axis, we have the fraction of molecules on the right. So the higher the curve, like right here on this blue curve, this is the most number of molecules moving at this speed. So in that sample, this blue sample, if we follow it down, this is the speed of the majority of the molecules in that sample. If we look at the red curve, we find the top right there looks like the speed of the majority of the molecules in that sample. Now, what this graph is showing is the same gas moving at 0 degrees in blue compared to 100 degrees in red. And we'll notice that in the blue, right, the majority of the speeds are there. In red, here's the majority of the speed. So we see that there was an increase in speed, which makes sense because there was an increase in the temperature. Now, when we talk about how fast molecules move, we know that the temperature is related to their average kinetic energy, but the molecules themselves can have different speeds, right? So when those two atoms collide, and this one flies off really fast and the other one has like slowed down, that's okay, that's normal. We use UMP, UAV, and URMS in order to describe these things. So UMP is the most probable speed. Most molecules move that fast. The UMP is the top of the curve. So remember, this is the fraction of the molecules. So at the top of the curve, this column, these are the most molecules. They're moving at that speed right there. Okay. UAV is the average speed of the molecules. It takes every speed from every one of these fractions, right, and it adds them all together and divides, and you get an average. It's actually usually a little higher than UMP, right, the most probable speed. And then there is the RMS, the root mean square speed. And this is the one that we talk about when we talk about kinetic energy. The RMS speed is one that we're going to calculate. So we have 4 particles with speeds of 4, 6, 10, and 12 meters per second. Let's just find the average speed first. So the average speed is easy. We have 4 of them. So we're going to divide the sum by 4, right? 4 plus 6 plus 10 plus 12. Well, 4 and 6 make 10, 10 and 10 make 20, 20 and 12 make 32, a fourth of 32. Our average speed, all right, would be 8.0 meters per second. Well, what about our root mean square speed? So first, let's look at root mean squared. So mean tells me I'm still doing the average. But squared says I need to square all these numbers, and then root tells me I need to take the square root of all of them. So RMS, it tells me exactly what to do. Take the square root of the mean of those speeds. So 4 squared plus 6 squared plus 10 squared plus 12 squared. Just like that. That's going to give me the square root of 74, all right, which is about 8.6 meters per second. Now, for an ideal gas, just something to throw in there that you can tuck away. For an ideal gas, the average speed is going to be equal to 0.921 times U, that energy there. This is something that's mentioned in your book. I've never seen that on the AP test, but I always mention it because I feel like it's an interesting little spot, right? That URMS, okay? URMS. Now, notice these two things aren't the same, right? They're different. They're not wrong. It's just that when we look at that equation, right, here is going to be my UMP, my most probable speed. Here's going to be my what do we call it? AV, my average, makes sense. And this is going to be my URMS. They're not going to be the same number. That's okay. All right. The RMS and the molecular mass are actually pretty well related. So you can relate the root mean speed and molecular mass using this equation right here. Make sure you remember this equation. It's the square root of 3RT over the molar mass. You can solve this out and find that 1/2 mu squared, all right, is going to give your kinetic energy, which is cool, all right? Which actually we usually just write energy. Something that we could solve pretty easily for there. The big point, though, is not really the formula as much as it is what it means, okay? So if a gas has a low mass, the speed is going to be greater. If the gas has, a high mass, then it's obviously going to be slow. This is the equation that backs that up, all right? So that's what we use it for. So if we look down here at this graph, all right, we can see that O2 is, got a speed down here. It's pretty slow. Oxygen's pretty slow. It's 32 grams per mole. N2 is 14, and 14 make like 28 grams per mole, so it's a little faster. H2O is like 16 to 18 grams per mole. It's a little faster. Helium is way faster, right? It's like 4 grams per mole. Hydrogen is like 2 grams per mole. It's even faster than that. So as the mass of the atom or of the gas decreases, all right, it gets faster and faster. And we talked about that last year. We talked about effusion and diffusion, right? So effusion is when gas moves through a tiny hole. It only happens when the gas actually encounters the pinhole. Diffusion is the spread of one substance through space or through another substance. We can see that the net distance traveled is from point A to point B here. But because it's a gas, there's a lot of different ways for it to get there. The smaller the gas, the easier it is for it to find its way through. So Graham's law, which we talked about briefly last year, but we really didn't get into any further, now we can kind of build on that. It relates molar masses of two gases based on their speed. The lighter gas is always going to travel faster, right? So R1 over R2, that's the rate of speed, is equal to the square root of molar mass 2 over molar mass 1. Notice the 2's are on opposite sides of the 1's, right? They're like set up for cross multiplying. So the RMS equation here, there it is right there, U equals RMS, that equation, this equation down here, all right, and this equation here are all telling us pretty much the same thing. Heavier gases move slow, lighter gases move fast, okay? They have a higher rate of speed. Now, ideal gases don't exist, not really. Real gases kind of behave like ideal gases as long as you have a hot temperature and you have a low pressure. But the moment you get outside of either a high temperature or a low pressure, you get some like really wild, deviations from this theory. You can see in this little inset here, there's actually your pressure can't even get up to 1 atmosphere, and your PV over RT value has to be at 1 in order, like here is where gases behave ideally. Outside of that, they start to deviate pretty rapidly. CO2 especially, right? It's like way down here, deviates pretty quick. Ideal gas is shown the normal behavior is this dotted line. So the further the lines are away from the dotted line, right, the greater the deviation. So why does this happen? Well, the assumption made in KMT is that there are no attractive forces and that the atoms don't take up any volume. Well, that's not true, all right? These little blue arrows here are showing you interactions between atoms that are impacting this red arrow right here. Notice that it's pretty thick, pretty solid in this left ideal gas. It's indicating that there's a high force, a high pressure when this atom right here, we'll call it atom 1, hits the wall. But in real life, atom 1 doesn't exert that much pressure because it's being pulled back by, atoms A, B, and C. The other thing is that in a low pressure system, right over here now we're looking at this picture on the left. In a low pressure system, yeah, the atoms of the gas really don't occupy a lot of the space. But as pressure increases and the volume decreases, right, the volume's gone down, the amount of space, like as a percentage occupied by those atoms goes up. It changes. And so the predictions that the ideal gas law creates kind of break down at those high pressures or at low temperatures. Because at low temperatures, right, low temperature is going to be over here. The lower the temperature, the slower they move. The slower they move, the greater time they have to interact with each other, right? So the greater the magnitude of this little blue arrow is right there. So how can we correct that? The ideal gas equation is corrected by something we call the van der Waals equation. We're going to look at that. And this van der Waals equation takes into account the van der Waals forces, things like dipole-dipole and dipole-induced dipole and polarity, that kind of thing. The volume adjustment that van der Waals also includes just comes to the fact that atoms do occupy space. So here's the van der Waals equation, right there. Now, compare it to PV equals nRT. They're obviously similar, right? PV, nRT. So we have two differences, two extra add-ins, and we can see them right here, all right? Here's A and here's B. Now, A, all right, is going to be a measure of the strength of attraction. So this is the strength of attraction. And it is going to actually account for the attractive forces between atoms, and it's going to adjust the pressure up. That's what that plus sign right there tells you. It's adjusting the pressure up. B is going to account for the volume of atoms. This accounts for the volume of the atoms. And it is going to correspondingly lower the volume of the vessel, right? It's going to lower the volume of the whatever is containing the gas so that it accounts for the volume of the atom. Now, we look up A and B, okay? You can see this on page 423 in your book. If I was going to give you a question like this, which I am, then you would obviously have this table or you would have the values necessary to do the problem. Let's look at one of those. So it says, estimate the pressure exerted by 1 mole of Cl2 in 22.41 liter vessel at 0 degrees Celsius, okay? So right off the bat, something that we should see, we should say, okay, the answer is 1. It's going to be 1 atmosphere. How do I know that? Well, I've got 1 mole of gas at 22.4 liters at 0 degrees Celsius. This is, STP is being described here. I have standard temperature, and I know it's 22.4 liters, and I have 1 mole. So my estimate is 1 atmosphere of pressure. However, we're going to calculate it using the van der Waals equation. So we would need to look up A and B, and I've already done that for you. A is in terms of liters squared times atmospheres over mole squared, right? And B is in terms of liters per mole, which is molarity, right? Concentration. So I know my equation, P plus, all right, N squared A over V squared, all right, times V minus NB equals nRT, okay? And I want to solve this for pressure. So take a minute. I want you to try to solve this on your own. Pause me, whatever. I'm going to go ahead and write out the answer, but I would recommend you try to solve this for yourself. So I'll give you a minute. Now, what are we going to do? Well, this is multiplied, so I want to get P alone, so I need to get rid of this right here first. So I'm going to divide nRT by V minus NB, and then I'll have P plus N squared A over V2 equals nRT over V minus NB, and I'll just subtract the N squared A over V squared. And that will give me pressure is equal to nRT divided by V minus NB in parentheses minus, right, because I had to subtract N squared A over V squared. Just a little algebra exercise there. Now I'm going to go through my problem. I'm just going to punch everything in. So pressure is equal to, this is going to be a long thing, 1.000 moles, all right, times 0. All right, I need my R, 082, and I'm going to be really specific, 06 liters atmospheres times mole inverse times Kelvin inverse times 273.15 K. All right, I'm going to close that bracket. And we are dividing that by V minus NB. So V is 22.41 liters minus N 1 mole. And B here is from our table. We looked it up. We have it at the top, 562 liters per mole. Minus, another square bracket, 1.000 moles squared, all right, times, I need A, which is up there at the top, 6.49 liters squared times atmospheres times mole to the negative 2 over 22.41 liters squared. All right, there we go. Close my bracket. Now, if I were you, what I would do is I would take my calculator, I'd punch that all in as one big problem, and I would solve it. I would do this problem on the left first, I'd do this problem on the right second, and then I would just subtract. That's what I did when I worked it out. And so I got 1.003 atmospheres minus 0.013 atmospheres. So the pressure is equal to 0.990 ATM. Now, something that's important to note, right? At low pressures, okay, and relatively high temperatures, the real gases behave similar to ideal gases. We have that proven right here. The ideal gas law tells us that this should be 1 atmosphere. We got 0.990 atmospheres. So the van der Waals equation accounts for the real interactions between those atoms. It obviously does lower the pressure just a little bit, but for the most part, it's right on track with the ideal gas law. So that's how you would solve one of those. All right. If you have questions, let me know. I'll be glad to give you a hand. That's the end of this lecture for the gas laws.